Hello students and welcome to the lecture. So students, as you can see here, basically in this lecture, we are going to start with the dual nature of matter and radiation. Okay. And this is going to be our part 1. In this lecture, we will talk about the particle nature of radiation, historical discoveries, photons, free electrons in metals. So these 4 points we are going to discuss here. Particle nature of radiation, the historical discoveries, photons, and the free electrons in metals. So this is going to be one of the important discussion for the physics. So please attend this lecture with full consciousness. But before starting this, there is a small disclaimer that we are required to understand before we proceed further. The disclaimer is the images used in a slide deck are for educational purpose only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the particle nature of radiation. So basically, the discovery of phenomena like interference, diffraction, and polarization of light established that light is of wave nature. Like whenever we talk about the light, if I ask you like what do you mean by the light, we generally in the layman terms connect it with the electricity that we are getting. Okay, but in the layman terms, in the terms of physics, the light is actually a form of energy. And whenever we do it by the means of physics, we always think that light is actually a wave or a radiation or a ray, you can say. Okay, because over the period of time, we have observed the phenomena like the interference, diffraction, and polarization. So that's why we established or we believe that the light is of wave nature. It is a way, you can say the radiation or the ray. But the Maxwell's equation of the electromagnetism and Hertz's experiment on the production and detection of electromagnetic waves that took place in 1886 strongly supported the concept of wave nature of light. Okay, like there are the two main scientists. First is Maxwell, second one is Hertz. He is a Maxwell, you can see. Okay, so basically they both did two different experiments. Maxwell did an experiment of electromagnetism and Hertz did the experiment on production and detection of electromagnetic waves in the 1886. Their experiment resulted in some equations, in some observations, and those supported the concept of wave nature of light further. In 20th century, the discoveries of photoelectric effect by Hertz, Compton effect by Compton, and star effect by Stark were explained by the quantum theory of light. Okay, so here 3 scientists we have discussed and their effects also. Like Hertz discovered the photoelectric effect, Compton described the Compton effect, and Stark described the Stark effect. So the discoveries of them actually got explained by the new quantum theory of light. Okay, so far we were discussing about the wave discovery. Like wave discovery is used, wave theory of light is used to talk about the interference, diffraction, and polarization. Further, the electromagnetism and electromagnetic waves production that also supported the wave theory of light. Later on in the 20th century, Hertz, Compton, and Stark, they did a different experiments. Like Hertz did the photoelectric experiment, Compton did the Compton effect, Stark did the Stark effect. These concepts or these experiments actually got explained by the quantum theory of light. This is not the wave theory, but the quantum theory of light, according to which the light consists of the packets of energy which travel in a straight line with the speed of light. Like Later on in 20th century, we further developed a way to look upon the light. We were no longer based on the belief of wave nature of light, but we actually also started thinking over the quantum theory of light. The quantum theory simply states that basically the light consists of packets of energy, and these packets of energy travels in a straight line with the speed of light, and that's why the light appears to be a wave or a radiation. Okay, but it's actually comprising a very small particles that we known as the quantums. Okay, and these are the packets of energy. Each packet of energy is called photon or quantum of light. So both the names could be used. Do not get confused that whether it's photon or quantum. You could use both the names. Okay. It is presents by hv equals to hc by lambda, where h is Planck's constant, v is the frequency of light, c is the velocity of light, and lambda is the wavelength of light. Thus, that's how the particle nature of light was established. Like in the initially, we were believing that the light is the radiation or the wave. Okay. And even we did the experiment that proved the thing as a right form, like the Maxwell and the Hertz. Later on in the 20th century, the three experiments that did by the three different scientists, photoelectric effect, why I'm repeating, so that you could recognize it later. Hertz did photoelectric effect, Compton did Compton effect, Stark did Stark effect. These discoveries or these experiments actually shifted our belief to the quantum theory of light, that the light is maybe seems as a radiation because it comprising a photon or quantum, that are the small packets of energy, travels in a straight line with the speed of light. As some phenomena of light were explained by the wave theory of light and some by particle nature of light. Hence, it was concluded that light is of dual nature. But there is an interesting thing. Like, however, our belief got shifted in the 20th century. But we still use wave theory of light and particle nature of light. Okay, why? Because none of these two theories is actually capable to explain all the phenomena of light. Wave theory could explain some phenomena, and some phenomena could not be explained by the wave theory. Simply, particle nature could explain some phenomena, and some phenomena could not be explained by the particle nature of light. Okay, so that's why to explain the phenomenon of light, we used both the theories, wave theory of light and particle nature of light. Okay, and later we concluded that light is of dual nature. It's a wave and it's also a particle. So both the things got explained later. Now you will be wondering, like, who is he? He's a Planck, Max Planck. Okay. Later on, the study of discharge through gases at low pressure led to discovery of many historical discoveries. Example, the discovery of cathode rays by William Crookes in 1879, X-rays by Röntgen in 1895, and of electrons by J.J. Thomson in 1897. Okay, so these rays also you can say comprising in the historical discoveries of lights. Okay, and it is actually you can say obtained from the study of discharge through the gases at low pressure. Okay, and please remember, like, who discovered which. Cathode discovered by William Crookes, 1879. X-rays discovered by Röntgen, 1895. Electrons discovered by J.J. Thomson, 1897. This is important because sometimes in the examination, maybe they did not ask you about the concept. Maybe they ask you about the thing, the discoverer, and the year of discovery. Okay. These discoveries help to understand the atomic structure J.J. Thomson predicted that the cathode rays are nothing but the stream of fast-moving electrons. Like if you see the cathode ray, okay, and if you really want to understand that what is comprised in that ray. So J.J. Thomson, after discovered the electrons in 1897, later on he said that cathode rays comprising nothing but these are the fast-moving electrons. Like electrons move fastly with the speed of light in a straight line, and that appears as a ray, but it is actually the fast-moving electrons, nothing apart from that. J.J. Thomson, using the mass spectrograph, experimentally determined the velocity and specific charge by mass of cathode rays. Based on the observation, he said this thing, that cathode rays is the fast-moving electrons. Got it? Remember what he used in the experiment? Mass spectrograph. For what? Determining the velocity, specific charge of the cathode rays. Got it? He concluded that the speed of cathode rays ranges from 0.1 to 0.2 times the speed of light. An accepted value of specific charge of cathode rays is 1.76 into 10's power 11 C by kg, which is independent of, means it is not depend on them, it is actually independent of nature of material used as cathode to generate the rays, nature of gas introduced in the discharge tube. This shows that cathode ray particles are universally alike because not dependent on the material of cathode use and not depend on the nature of gas. So whatever the material you use as cathode, whatever gas you introduce in the discharge tube at low pressure to emit these rays, okay, the cathode ray speed and the specific charge and value will not be dependent on these. So these why the cathode particles are universally alike. Okay, and the speed of cathode rays is also 0.1 to 0.2 times the speed of light, which proved by J.J. Thomson in his experiment. Later on, in 1887, it was also found that if certain metals were irradiated by ultraviolet light, the electrons were emitted having small velocity. It was also found that if certain metals are heated to high temperature, the electrons were emitted. These studies led scientists to think that electrons are fundamental particles and are universal constituent of matter. Okay, so the two things happen. These two things are to be understood first before moving forward. Okay, so the year was 1887 when, while doing a various experiments, it was found that certain metals, if they got irradiated by using which light? Ultraviolet light, then the electrons will be emitted. But these electrons were not fast moving electrons but having the small velocity. That was the first thing that observed. Second thing, it was also observed that certain metals having the capacity heated to high temperature, they emitted the electrons. And these two things actually made the scientists to think that the electrons are fundamental particles. Okay, it means that they are the most basic particles of any matter and also the universal constituent of matter. Like whatever matter you found, you will find the electron that side. Okay. Later on, Millikan, he is the Millikan, here you can see him, measured experimentally the charge on the droplets and predicted that the charge on droplet is always integral multiply of elementary charge 1.602 into 10's power minus 19 C, which is the integral multiple charge of an electron, that is 1.602 into 10's power 19 C. This shows that the charge on a body is quantized. So who proved that the charge of a body is quantized? millicurie. Okay, because when he experimentally tried to measure and predict the charge on droplets, he found it always as 1.602 into 10 power minus 19 C. And this thing is also the integral multiple charge of an electron, because electron multiple integral charge is 1.602 into 10 power 19 C. Okay. Now, after finishing the particle nature of radiation and the historical discoveries that took place on that time, let's have a discussion over the photons. One thing that I would like to make clear here, whenever you talk about photons, always remember that you are going to use the quantum theory of light. In wave theory of light, photons not used. Photons used mainly in the quantum theory of light. So whenever you see the photons anywhere, remember that you are going to start with the quantum theory of light. Okay. So before starting about the photons and how they are used in the quantum theory of light, we must understand that what are the photons in actual. So photons are the packets of energy. They are the packets of energy or energy particles, okay, which emitted by a source of radiation. So there is always a source of radiation from where the radiation is emitted, from where the ray is emitted. Okay. So as we know, in the quantum theory of light, it is stated that basically the wave that you are seeing, okay, that waves comprising a small energy particles that we call as quantum on photons, okay, which are moving in a straight line and moving with the speed of light. Okay, so which means if there is any source of radiation which emitting the ray, so that source is the source that is emitting actually the photons, are packets of energy or energy particles in a straight line with the velocity or speed of light. Okay, they travel in a straight line with the speed of light as per the quantum theory of light. Now, what are the main features of photons? Okay, we have know about the photons in a basic by definition. Packets of energy or energy particles moving with the speed of light in a straight line, emitting by the source of radiation which emitting the ray. Let's have a talk on their features. Like, what are their features? According to the Planck's quantum theory, a source of radiation emits energy in the form of photons, and these photons travel in a straight line. Okay, the energy of a photon is E equals to HV equal to Hc by lambda infinite, where H equals to Planck's constant, which is having the fixed value of 6.62 into 10 power minus 34 joule per second. V and lambda equals to frequency and wavelength of photon. C equals to speed of radiation. So just remember, this is the energy of photon, E equals to HV equals to Sc by lambda infinite. Just remember that which symbol is representing what. That is important. So H representing Planck's constant, which is having a value of 6.62 into 10 power minus 34 joule per second. V and lambda equals to frequency and wavelength of photon, and C equals to speed of radiation. At what speed the radiation is going on. Third feature, all photons emitted from source travel through space with same speed, equal to the speed of light. So suppose if we say there is a particular source of radiation that emitted 100 photons, for example only. Okay, so all these 100 photons will have the same speed, and all of them will travel in a same straight line with the same space. Okay, and the speed that they will acquire will be equal to the speed of light. It won't happen that 10 of them having the speed of light, 10 of them having the lower speed of light, 10 of them having a more speed of light. No. This ununiformity will not be noticed there. Okay. So remember, all the photons that are emitted from the same source of radiation travels through same space with same straight line with the same speed. The speed is equal to the speed of light. The frequency of a photon gives the radiation a definite energy or color, which does not change when photon travels through different media. So remember, whatever the frequency of photon will be, that defines the radiation, a definite energy or the color of that particular radiation. And whatever medium the photons travel, okay, whether they're traveling from the vacuum, air, glass, and whatever you can say, okay, the medium, that thing will not change. The frequency of radiation, energy, which is indefinite, okay, that will not change. The velocity of photon in different medium is different, which is due to change in its wavelength. Okay. So what will change because of the change of medium? The velocity of a photon. That will change. Okay. Due to change in the wavelength. And nothing will change. Photon has zero rest mass. It shows that photon cannot exist at rest. The equivalent mass m of a photon of frequency v is given by energy equals to mc square equals to hv dash or m equals to hv by c square. The momentum of the photon equals to mcc minus hy equals to h by lambda. So remember, the photon having a zero rest mass, so it means the photons will always in a traveling. They could not exist at rest. This thing make clear in your mind. The photons could not exist at rest. They will always be in a traveling or emission. The energy of photon is usually expressed in electron volt, EV, where 1 EV is the energy gained by electron when it has been accelerated under a potential difference of 1 volt. 1 EV equals to 1 electron into 1 volt because it is the energy gained by the electron when it travels under the acceleration due to the potential difference of 1 volt, which is 1602 into 10's power 19C into 1B equals to 1.602 into 10's power minus 19J. Photons are electrically neutral. Okay. They do not carry any charge, whether positive or negative, they do not carry any charge. If they are not carrying any charge, so that's why they are not deflected by any electric and magnetic field. Under suitable condition, the stream of photons may show the phenomenon of diffraction. There's a note. Photon is not a material body, but it is a packet of energy. The intensity of light depends upon the number of photons present in light. If the number of photons more, intensity of light more. If the number of photons less, intensity of light less. Now, free electrons in metals, if we talk about, in metals, the electrons in the outer shell called valence electrons of the atoms, these are loosely bound. They are quite free to move easily within the metal surface but cannot leave the metal surface. Such loosely bound electrons are called the free electrons. The free electrons in metal could move about freely inside the metal but could not leave its surface because they required energy so that they could be emitted. There is a potential barrier due to the attractive force called the restraining force on the metal surface, which has to be overcome by the electron to just escape from the metal surface. In order that an electron may just leave the metal surface, a certain minimum amount of energy has to be supplied to the electron, which depends upon the properties of the metal and the nature of the surface and termed as the work function of the metal. Thus, the work function of a metal is the minimum energy that is required by an electron to just escape from the metal surface so as to overcome the restraining force at the surface. Work function of a metal is generally denoted by the delta zero and it is usually measured in EV. Note, work function is lowest for Kcm, where delta 0 equals to 2.14 eV, and highest for platinum, where delta 0 equals to 5.65 eV. It means metal KCm could eject electrons with the light of lower energy and platinum with higher energy. So with this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.